everybody. Welcome to class. Grab just a couple things. There's the usual attendance link. Please go fill it out. I'll post it again in a little bit, but you can always just bookmark it if you want it. Similar to number 7, let me just grab his homework real quick here and I will take a look. I feel like I did a video like that, but let me double check. I should bookmark his homework instead of having to click through every time here. All right, let's see. Homework 2, number 7. So I definitely did do a video with an example like this. I can do another example, but I wanted to remind you guys, like there are examples like this that you should totally go watch because it'll be helpful. But yeah, we can definitely do an example. So I feel like his example, his question is almost too easy. Like it's pretty straightforward. I mean, I know for me, it's a little too easy because I've seen a lot of these. I'm sure it's not the same for you guys. So we can totally do an example like that. Let's look at something like, let's say we had, sorry, my chair. I always want to put my chair over to my right, but there's like no room over there, so I need to pull it over to the left. Okay, so let's see here. So let's say we had a sequence, a recursive sequence, or a difference equation, given by something like a sub n plus 1 equal to, and I can make it very similar to this problem. We can say, let's say it's like 1/6 of a sub n plus, I don't know, what am I going to do here? Something crazy. What's that? Let's say that was our difference equation. And let's say, I don't know, I'm going to make something up that's probably not going to try to be great. Let's see. I want something like, sorry, I'm just going to make this turn out okay. Sure. Let's say a sub 1 was 18. And our question is, what is the limit of the sequence? And once again, here is the, here's the link to the attendance one more time, everybody. So the final limit of the sequence, you don't really, I mean, you kind of need to know where you start, but for these questions, we'll learn more about it later. You could start plugging in and say, okay, if A1 is 18, then, grab a different color here. A sub 2 is going to be 1/6 of a sub 1, which is 18, plus 9. 1/6 of 18 is 12. Sorry, 1/6 of 18 is 3, and 3 plus 9 is 12. And then we can plug that in to find a sub 3. A sub 3 would be 1/6 of 12, which is 2, plus 9, so that's going to be 2 plus 9, which is 11. And then a sub 4 would be 1/6 of 11 plus 9, which isn't very nice. It's a little bit smaller than 11, right? Because 1/6 of 11 is a little bit smaller than 2. So I'm not going to say like this is just less than 11, a little bit. But this isn't the way to get there. Oh, blurry? I'm sorry. That's not good. Maybe let me try wiping off my camera. Also, so if you guys are saying stuff and let me grab some tissues. Sorry. No. I think my volume's on. Let me double check here. Okay, it should be on. So you guys are typing things and I'm not seeing it. Feel free to just say something. Let me try wiping my camera here. Sorry, I know, I'm sure that's terrible. Did that help at all? Does it seem less blurry?
No, it said your bandwidth was low.
Oh.
Or internet was low or something.
Be on the wrong Wi-Fi. Let me double check. Okay. Let me try switching to. My wife and I are lucky that she is on a different Wi-Fi system than I have, but sometimes my computer just wants to join her network. So one quick second here. Sorry about that. So anyway, while I'm doing this, you guys can figure out what you're supposed to do over there. So you're supposed to try and take the limit of that by substituting in L for all the a sub n's. So is that better? I hope so. I'm getting a message saying my internet connection is unstable. So better, not better? Anybody?
It looks about the same.
It has, yeah.
So it doesn't look better?
It just looks the same.
Okay. Can you read it at all?
It's very blurry.
Okay, I'll try.
No, it's very blurry.
So I'll try and write bigger. Unfortunately, I don't think the document camera is going to be a better option because it also doesn't look great. But so the good thing is my video still looks all right when and it's recording locally to my computer. So even if it looks blurry over your internet connection or my internet connection right now, I should still be able to upload it and it shouldn't look too blurry. So I'll try and say all the words and hopefully you can kind of read the things I'm writing. But yeah, unfortunately, I don't think I have a better solution. So we will go with this. So again, I've got a sub n plus 1 equal to 1/6 of a sub n plus 9. And the idea here is that I want to take the limit of this. So the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of a sub n plus 1. Right? If a sub n is just the nth term of the sequence, it doesn't matter if you're at the nth term of the n plus 1 term. If you're letting n go to infinity and the limit exists, they're both going to end up at the same place. So the idea is that you're going to take this equation and just replace each of these with what you're calling the limit, which we usually use capital L. You can actually show the work. I don't think you really need to, but you could say on the left-hand side, the limit as n goes to infinity of a sub n plus 1 equals to, on the right-hand side, the limit as n goes to infinity of 1/6 a sub n plus 9. And then we can use limit rules to say, oh, the limit of 1/6 times a n plus 9 is just the limit of this plus this. So it's the limit as n goes to infinity of 1/6 times a n plus the limit as n goes to infinity of 9. But then this constant 1/6 can come out in front of the limit, right? That's one of those limit rules. If you have a limit of a constant times the sequence, constant come out in front. And then here's what we get. The limit of a sub n plus 1 is just the limit. I'm going to call it L. And it's equal to 1/6. The limit of a sub n is also just L. And then the limit of 9, the limit of a constant is just the constant. So although I did a lot of work for this, you shouldn't do all this work unless he asks you to. The idea behind this every time is just wherever you have an a sub n plus 1 or an a sub n, you're just going to plug in L and you're going to solve. So I'm going to subtract 1/6 L. So I have L minus 1/6 L equal to 9. 1L minus 1/6 L is 5/6 L equal to 9. And then multiply both sides by 5/6 to get L equal to 9. Sorry, multiply both sides by 6/5 to get L equal to 9 times 6/5, which ends up being 54/5, which is just a little bit less than 11. So that's kind of the idea of how you would solve one of these. Let me do another one, because they do, usually we see different ones. So let me give you guys one more here. Let's say, this is kind of the version I like. Let's say a sub n plus 1 equals, let me think for just 1 sec so the numbers aren't terrible. Sorry, one moment please while my brain works. 8 over, sorry, minus, I have to think, 1 sec. No, minus 7. Right. So let's look at this. So I've got, again, I'm going to do this short way this time. So I'm just going to replace my a sub n with l. So sorry, guys, this is a sub n plus 1 equals 8 divided by a sub n minus 7. So replace this and that with your limit L. And then L is equal to 8 over L minus 7. Multiply sides by the denominator. L times L minus 7 equals 8. Squared, or not squared, multiply this out and subtract 8. So you get L squared minus 7L minus 8 equals 0. And then solve this by factoring. So you get L minus 8 times L plus 1 equal to 0. And so then, solving for L, you get L equal to 8 or L equal to negative 1. So the question is, and so you guys might not actually cover this, I don't know. But the question here is, which of these is the limit? Because they can't both be the limit. So if you're talking about a limit of a sequence, you can only ever have one limit value. So which of these is it? Well, sometimes it depends on where you start. And I want to make sure this one actually works out just fine. So let's say let's kind of split the differences. Then let's say we start at a sub 1 equal to, I don't want to pick something that's awful. Let's try 5. I don't want to try 6. Let's try 5. So if a sub 1 is 5, then a sub 2 is going to be 8 over 5 minus 7. 8 divided by negative 2 is negative 4. All right, so let's find a sub 3 now. A sub 3 is going to be 8 divided by a sub 2, negative 4 minus 7. 8 over negative 11, or negative 8 elevenths. That's a little bit less. So definitely, if I had to guess at this one, I would say I'm probably getting closer to negative 1. So I plugged in 5, I got something negative, and then I got something negative. Let's see if I get something negative one more time. A sub 4 equals 8 over, so I'm plugging in negative 8 elevenths minus 7. That's definitely going to be negative because the bottom is negative, right? It's negative 8 elevenths minus 7. So my guess is that 8 definitely is not the limit. This isn't getting closer and closer to 8 if I start at 5. And it's probably getting closer and closer to negative 1. I can calculate this. It's 8 divided by negative 8 elevenths. Minus 7 is minus 77 elevenths. And simplifying that, I have 8 divided by negative 8 minus 77 is negative 85 elevenths. Flip and multiply, you get 8 times 11 over negative 85, which is negative overall 88 over 85, which is pretty close to negative 1. So yeah, my guess here, it's not for sure, but I know it is. The limit here is definitely negative 1. So if you have two possible values for your limit, you have to choose, and it's going to depend on what value you started at initially. In this case, we started at 5, although it seems like we might get closer and closer to 8. We didn't. In fact, I will point out here, you actually can't have 8 be the limit of this sequence. If you started at, say, somewhere bigger than 8, like 9, right? If we started at a sub 1 equal to 9, then a sub 2 would be 8 over 9 minus 7 is 8 over 2, which is 4. Then you plug in 4, you're going to get a sub 3 equal to 8 over 4 minus 7, which is 8 over negative 3. We're still getting pushed back towards those negative values. So here, negative 1 definitely is the only limit, and 8 is not a limit. It's kind of neat. That's probably true. I'd actually have to do a little more work to verify that that's actually absolutely true, but I'm pretty sure. Here is the attendance link again. So hopefully, does the screen look any better, or is it just terrible still?
It looks better.
Oh, good. Glad. That's good. All right. So what else would you guys like to talk about? Are there any other questions from the homework that are challenging that we should cover, or should we move on to other things?
Maybe like another squeeze theorem example?
Definitely. So in my mind, there's two different types of squeeze theorem problems we typically encounter. I know he did one kind of like this today or on Friday in class when he was talking about continuity. So one type of example is when you have a limit to infinity. So limit, let's say x goes to infinity. And you have something that essentially looks like a rational function, except there's a sine or a cosine in it. So you have a limit as x goes to infinity of 2x to the fourth. What have I got here? I don't know. Sorry, my brain. Minus 5 sine of x over 7x to the fourth plus x cubed. And if that sine of x wasn't there, right, if it was just minus 5 or minus 5x or minus 5x squared, then, yes, we can look at number 4 for sure. Then this limit would just be 2/7 because it's a rational function where the quotient, the limit of leading coefficients is 2/7 and the degrees are the same. But here we have the sine of x, which is causing a problem. So the way I would encourage you to kind of look at this is this sign between 1 and -1. And so you can kind of actually just take this whole thing and say that this whole expression is between the same thing with a -5 and a +5 here, right? Just kind of thinking of sine being 1 or -1. Now here's kind of the work behind it. We say that sine is between 1 and -1. And then we try and make this look like all of this. So I multiply everything by -5. So -5 times -1 is +5. Bigger than or equal to -5 times sine of x is bigger than or equal to -5. Right? I switch the order of the inequality because I multiply by a negative instead of a positive. You could rewrite this though as -5 less than or equal to -5 sine of x less than or equal to 5. And then I'm going to add 2x to the fourth to everything. So 2x to the fourth minus 5 is less than or equal to 2x to the fourth minus 5 sine x is less than or equal to 2x to the fourth plus 5. And then I divide everything by this denominator. 7x to the fourth plus x cubed. 7x to the fourth plus x cubed. 7x to the fourth plus x cubed. So whenever you're thinking squeeze theorem, your first job is always to get the thing you're trying to take the limit of between two other things that we're able to take the limit of. So once you've done that, then we can say, okay, I'm going to look at the limit of this. The limit as x goes to infinity of 2x to the fourth minus 5 over 7x to the fourth plus x cubed is 2/7. Similarly, the limit as x goes to infinity of 2x to the fourth plus 5 over 7x to the fourth plus x cubed is 2/7. And then we can say, I'm sorry, that's included over there, apologies. By the squeeze theorem, or the sandwich theorem, whatever you want to call it, the limit of the thing in the middle, right? Since the limit of this is 2/7 and the limit of this is 2/7 and the same, and this is between those two things, its limit is also 2/7. So the limit is x goes to infinity of 2x to the fourth minus 5 sine x over 7x to the fourth plus x cubed is 2/7. And that's how we do that. I gotta tie my shoe, otherwise I'm gonna trip. Tie my slipper, actually. It's not a shoe. But those shoelaces coming undone. Okay, so stay tight. All right. Should we do another squeeze theorem one, or is that kind of what you were asking for? There are other types of squeeze theorem problems. Okay. So I'm going to move on. So I also did do a video with a horizontal asymptote, I think. It's similar to problem number 4. It's not exactly the same. I feel like his problem is kind of extra gross. But we can definitely do a similar problem to it. These ones are always kind of just a giant pain. So I will point out that for this, we definitely did one like this in class as well. Sure. So we can do another one. Let me switch back and forth. Though. Let me look at a problem similar to problem 4, and then we'll go back to a problem similar to another squeeze theorem problem. So we've got the limit, and I am going to change it up a little bit because I want it exactly. As x goes to negative infinity of, what do we got here? X over the square root of 9x squared. Sorry, I gotta think for a minute here. Plus 4 minus 2. Okay, it's very, very similar to how his is written. That's a 4. Sorry, 4 looks terrible there. Okay, so whenever you're dealing with a limit and you see a square root minus something else, or something else minus a square root, it's usually it's a pretty sure thing that you're going to have to multiply by the conjugate. So when you have a square root minus something, the conjugate of that is the square root plus the same something. And if your thing was the square root plus something, then your conjugate would be the square root minus something. So something plus something and that same something minus the same something, these are conjugates. And I definitely did some videos of conjugates as well with an example, I think, kind of like this. So if you need help with conjugates, there's a video, you should definitely go watch it. They're all short videos, so like they shouldn't take too long to watch. And hopefully I'm not too terrible in the videos. And the reason we multiply by a conjugate is because when you multiply by a conjugate, or I should say when you multiply conjugates together, a plus b times a minus b, you get a squared minus b squared. And the middle terms cancel out. So why we are multiplying by the conjugate. So here, I'm going to multiply by the conjugate of the thing that makes sense to multiply by the conjugate, the square root thing. I'm going to multiply by the square root of 9x squared plus 4 plus 2, and then it has to be the same thing on top, because we're really only allowed to multiply by 1 without changing anything. Okay, so. Also, I really enjoyed some of the math jokes you guys sent me. Keep them coming, they're funny. I like them. So then, whenever you're multiplying by a conjugate, you want to multiply the conjugates. Right? This thing here times this thing here. If I'm thinking of this is my A and this is my B, when the thing I just erased, then the result should be this squared minus this squared. So it should be this square root squared. So that's just, I feel like I'm doing something so wrong. I'm sorry, I've led you down the wrong path, and I apologize for that. So often it's good to multiply by the conjugate. That is not the case here. It's totally unnecessary. I mean, you could, so it's not wrong to multiply by the conjugate here, but it's actually not what we need. I am sorry, this problem is easier than I made it out to be. Let's back up. So just to point out, if you did multiply by the conjugate, here's what you would get. I'm going to erase this because we don't actually need this, but just to show you the work. So the top you just leave as the thing times the other thing, right? They're not conjugates, we shouldn't multiply it out. The bottom, if you were multiplying it out, you get 9x squared plus 4. The middle terms you cancel, and you get minus 2 squared. And then you could cancel the 4 here and the 4 there. But again, that's really, I mean, yeah, we could do that, but that's dumb. So we shouldn't have done that. Oh well, sometimes we make mistakes. This one is easier than I made it out to be. So the idea here is when you have a square root of something with this x squared in it, the idea is you want to factor out the x squared from inside the square root. So I've got x squared times 9x squared divided by x squared is 9. And 4 divided by x squared is 4 divided by x squared. So if I distribute that x squared back through, you get 9x squared plus 4, which is exactly what I have there. Sorry, it's kind of a, I feel like, I just want to make sure I'm not doing something dumb. No, I guess that's right, okay. Sorry, these are weird. And then the reason we factor out the x squared is so we can take the square root of x squared. So I'm going to break this up. Okay, so the square root of x squared times the square root of 9 plus 4 over x squared minus 2. Okay, so then what's the square root of x squared?
Absolute value of x.
Yeah, exactly. So that's going to be the absolute value of x. You get the limit as x goes to negative infinity of x over the absolute value of x times the square root of 9 plus 4 over x squared minus 2. And then, since x is going to negative infinity, the absolute value of x is negative x. So we're going to write this as the limit as x goes to minus infinity of x divided by negative x times the square root of 9 plus 4 over x squared minus 2. Okay, then we're going to divide everything by x. So I'm going to have the limit as x goes to minus infinity of, on top I'm going to have x divided by x. On the bottom I'm going to have this thing, negative x square root of 9 plus 4 over x squared divided by x minus 2 divided by x. And then I think I've got enough room down here. So we saw the limit as x goes to minus squared. I'm writing the limit every time until I actually get a numerical answer. X divided by x is 1. X divided by x cancels here and I'm left with negative square root of 9 plus 4 over x squared and minus 2 over x. Now, as x goes to minus infinity, 4 over x squared goes to 0 and 2 over x goes to 0. So I'm left with 1 over the square root of, the negative square root of 9 plus 0 minus 0, which is 1 over negative 3, or negative 1/3. And I'll just tell you, if this had been the limit as x goes to positive infinity, you would have had a positive x here instead of a negative x, and the limit would have ended up being positive 1/3. So if you look at this question, so looking at his homework, right? Homework question 4, I would imagine your limit will end up being positive 1/2, or sorry, negative 1/2. And then if you look down at question 8, it says to find all the horizontal asymptotes of that same function. So the horizontal asymptotes of this function would be negative 1/3 and positive 1/3, because if you did, I'll just say, the limit as x goes to positive infinity of this function would equal positive 1/3. So the horizontal asymptotes of this function would be positive 1/3 and negative 1/3. And I have to go turn off the heat because it is too hot in here. Okay, so, oops, dropping things. Okay, someone asked for another squeeze theorem question, and I think after that we should maybe start talking about limits and continuity. So the other type of squeeze theorem isn't a limit to infinity. Usually it's a limit, it's usually approaching 0. So something like the limit as x approaches 0 of x to the 6th times cosine of 1 over x cubed. Where if you look at cosine of 1 over x cubed, it's totally undefined as x is closer and closer to 0. It's in the same kind of way that sine of 1 over x is totally undefined as x is closer and closer to 0. If you want, we could even look at the graph of it on Desmos. Just one second here. Awesome, yeah. So let me share my screen with you guys. I remember how to do that. Yeah, okay. I can minimize that, sorry. Here's the graph of cosine of 1 over x cubed. And you can see it gets super ridiculous in the middle there, right? And if we zoom in a little bit, like, oh yeah, it's doing the thing where it just bounces back and forth between 1 and -1 all the time. So just like with the other example of what's the word I'm looking for? Sorry. The other example of the squeeze theorem, you're not always, but like 90–95% of the time, you're using the fact that cosine of whatever or sine of whatever is between -1 and 1. So I'm going to start off by saying, oh yeah, cosine of 1 over x cubed is between -1 and 1. I'm going to change this problem just slightly because I want to make it a little bit more complicated just so that I can show you guys something that you have to be extra careful of. Do I actually? No, not really. Okay. So then we're going to multiply everything by x to the 6th. So -1 times x to the 6th is -x to the 6th. X to the 6th times cosine of 1 over x cubed, and I'll I wrote to the 5th there. Less than or equal to 1 times x to the 6th. All right, and then we take the limit of the outer parts. And just like before, the limit as x goes to 0 of -x to the 6th. I should say, like before, meaning the limit of this side and the limit of this side are going to be the same. The limit of this side is 0. The limit as x goes to 0 of positive x to the 6th is equal to 0. And so then, since these limits are the same value, right, they have to be the same. If they're even different a little bit, we can't say the squeeze theorem does anything. But these give us that by the squeeze theorem, the sandwich theorem, the limit as x goes to 0 of the inside function, x to the 6th times cosine of 1 over x cubed, has to be the same value, which is 0. So that's how we apply the squeeze theorem there. But generally, what I look for if I'm thinking squeeze theorem is I'm probably looking for a cosine or a sine to be between -1 and 1. And just to kind of show you what the graph of this looks like, so share my screen again. If we look at the graphs of, so here's x to the 6th, which is kind of crazy looking. And here's -x to the 6th in blue and in green. And then if we take our red function and we multiply by x to the 6th, look, it gets smushed between the blue and the green function so that its limit has to be 0. You're still getting all these little oscillations, but their amplitude is being tamped down because it's between x to the 6th and -x to the 6th. So hopefully that again kind of helps you see what's going on with the squeeze theorem. All right, let me stop sharing the screen. So what else? Oh, I see that there were questions about other problems from the homework. Let's see. Okay. Let me take a look here. Sure. So I don't think, okay. So for number 9, I definitely made some videos they're very much the same as that problem. So I would encourage you to go look at the video about horizontal and vertical asymptotes. But we can certainly look at 6. The 6 is kind of leading us in a direction that we want to go. So probably today in class, he's going to start talking about the definition of the derivative and how you're going to find the limit as h goes to 0 of some quantity. My shoe just keeps going untied. I mean, it's been like this like as long as I've had these slippers, but I wish it wasn't. Okay. So let's take a look here. Yeah. So we're looking at the limit. And I'm going to give a little bit more big picture here because I think it's worthwhile. So, and actually, let me give you guys the attendance form one more time in case you didn't get a chance at it. So the idea here is that, how big picture do I want to go? So this problem, to me, let's see, yeah. So to me, this looks like we're trying to evaluate this limit. The limit as h goes to 0 of f of, sure, I would call it f of 3 plus h minus f of 3 all over h, where the function is, and I'll use the same function, sure. It's the square root. Do I want to use the same function? Not really. This function is something. I'm going to make a particular function. Let's say the function is, sorry, I thought I had a good idea of how this is going to go, and then I didn't. Lame. Sorry, I got too caught up here. Let's make it easier. Let's say it's x squared minus 8. So I'm trying to evaluate this sort of expression for this particular function. And here's the idea that's always going to happen. When you evaluate a limit like this of a difference quotient, we should always be able to make this h in the denominator cancel out, which is good because it's going to 0, which would be a problem. So what we're going to do is we're going to say, okay, well, f of 3 plus h is just 3 plus h squared minus 8, which we could simplify, but we're not going to. F of 3 is just 3 squared minus 8. Okay, we can simplify that. That's 1. So then looking at this limit here, this limit as h goes to 0 of f of 3 plus h, well, that's 3 plus h squared minus 8 minus 1, right, because that's f of 3, all over h. Let me just point out, there's f of 3 plus h, there's f of 3. And again, the idea here is always to make all the non-h things. So if you've seen difference quotients before, we're still doing the same sort of work we did before with difference quotients. We're trying to make all the things that don't have an h in the top cancel out. So then if the rest of the things have an h, you can factor out an h and then cancel the h in the bottom. That's what's going to happen here. Take the limit as h goes to 0. 3 plus h quantity squared is 9 plus 6h plus h squared, right? It's 3 squared plus 2 times 3 times h plus h squared minus 8 minus 1 all over h. But 9 minus 8 minus 1 is 0, so this cancel out. And look, all the not h things cancel. The rest of the things have an h. The limit as h goes to 0 of 6h. Oh, that's good, yeah. Plus h squared all over h. And then that'll be the limit as h goes to 0. I can factor an h in the top. You can also just think of dividing each thing by h. The factor on h in the top, I'm left with those h's canceling, so I'm left with 6 plus h. And then finally, the limit as h goes to 0 of 6 plus h is just equal to 6, because it's 6 plus 0. So that's kind of where we're going towards with this question 6, I think, from the homework. Is he leading us in this direction of, oh, we're going to be evaluating these limits because these limits are the limit definition of the derivative. We can, and let's actually look at an example that's similar to the one in the homework just because it's a little complicated. So here's one that's pretty similar, but not quite the same. But what you should always see with these kind of limits is if you just plug in 0 for h, you should just have a 0 over 0 type of limit. And that's true. So if I look at the limit.
Last problem, why was it 6 and not -6?
Because I might have made a mistake. Double check. No, it's definitely 6. So it's 6 because, well, right, because it's, so when I do 3 plus h, I get, or 3 plus h squared, I get 9 plus 6h plus h squared, right? That's definitely a plus there. And then, right, so when I cancel out the constants, so I'm left with 6h plus h squared. I factor out an h, I'm left with 6 plus h. And then I'm not solving for h, so I'm not trying to say this is equal to 0 and solving for h. This h here is going to 0, right? And letting h go to 0. So I'm getting 6.
Oh, okay.
Which is equal to 6. That's what's happening there.
All right, thank you.
So, we look at a similar example. We do something like the square root of, I don't really matter here. Doesn't matter. Yeah, a little bit. Sorry, I just want to make sure this isn't super dumb. Yeah, I'll just make something up. So let's say it's 5h squared plus 7h plus 16 minus 4 all over h. And as you can hopefully see, it's a 0 over 0 type of limit. If I plug in 0 for h, I get 0 plus 0 plus 16 squared root of 16 is 4. 4 minus 4 is 0 over 0. And so here we are going to multiply by the conjugate. So the conjugate of the square root minus the thing. Oh, actually, let me change the problem just slightly. It'll still be the same, but I want to do the subtraction in the other order just to show you guys an extra little piece. Let's say we had instead 4 minus that all over h, and still taking the limit. Still a 0 over 0 type. Right? 4 minus 4 is 0, h is then 0. And then we're going to multiply by the conjugate, which is 4 plus this whole square root. So we've got that times that. And then we're going to multiply them out. And again, when you're multiplying out conjugates, so we're multiplying the top and bottom by the conjugate, you don't want to multiply out the things that aren't conjugates. I don't want to distribute this h. I don't want to get 4h plus h times all this. I just want h times all of that. And the reason why is because I'm looking to make this h cancel out. So it doesn't make sense to distribute it. On top, we multiply conjugates. So we multiply conjugates to get the first thing squared minus the second thing squared. Now here's the thing, it's minus all of it, so you have to have parentheses around it so you can distribute the minus sign. If you don't get the not h things to cancel out, it's probably because you forgot to distribute the parentheses here. So it's going to be the limit as h goes to 0 of 16 minus 5h squared minus 7h minus 16 all over the same denominator. These 16s cancel. And then negative 5h squared minus 7h, each have an h in them, so you can divide by h and get the limit as h goes to 0 of negative 5h minus 7 all over 4 plus the square root of 5h squared plus 7h plus 16. So the step that I kind of skipped there was factoring out the h on top. So really I could say this is h times negative 5h minus 7, and then canceling that h that factored out with that h down there. And then finally, the rest of the h's get to go to 0. So I end up with negative 7 over 4 plus 4, which is negative 7/8. So that's the idea behind that kind of problem. Let's see, what else do you guys ask about? So problem 10, we definitely did a problem like that today. That first squeeze theorem problem we did was definitely similar to problem 10. There's also, I think there's a video with a squeeze theorem problem like that as well, so you should go look at that for more examples. For problem 5, the limit is x goes to 0. So if I have a function like this, for x cubed when x is less than or equal to 0, and 1 minus x squared when x is bigger than 0, there's a couple ways to see that this limit, well, to tell what this limit is or if it doesn't exist. But the usual way, the way they kind of want us to do it is to show that the limit from the left and the limit from the right either are or are not equal. And that's usually what we have to do when we're trying to show what a limit is if you've got a piecewise function that's different on either side of 0. So I'm trying to find the limit as x goes to 0 of f of x. I have to look at two pieces. The limit as x goes to 0 from the left, and the limit as x goes to 0 from the right. So if I'm approaching 0 from the left, that means I'm less than 0. And I have to use the piece of the function where x is less than 0. So I'm looking at this piece here because x is less than or equal to 0. So that's going to be the limit as x goes to 0 from the left of 4x cubed. But 4x cubed, we can just plug in 0. So I'm going to get 4 times 0 cubed, which is just 0. So look at the limit as x approaches 0 from the right. We have to pick the piece of the function where x is bigger than 0, which is this piece. So we're going to pick this piece. So that's going to be the limit as x approaches 0 from the right of 1 minus x squared. But again, we can just plug in 0 because these rays are undefined anywhere. That's going to be 1 minus 0 squared, which is 1. Now, since the left-hand limit and the right-hand limit are not the same, right? These are definitely not equal to each other. That means the overall limit doesn't exist. So limit as f of x, limit as x of 0 of f of x does not exist because the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches 0 from the right of f of x. However, if the function was instead 4x cubed plus 1, then this would have been 4x cubed plus 1. This would have been 0 plus 1. This would have been 1. Then the limits would have been the same. Then the limit would have existed, and it would have been 1. So if they're different from either side, limit doesn't exist. If they're the same, limit does exist. Let's see. All right, what else in the last couple minutes we got here? Okay, so actually I have something I want to say. So here's where we're going. He definitely talked about continuity. So I want to give you one kind of example, even though he doesn't really do a lot of examples, which is too bad. But let's look at, say, this function. F of x equal to, let's make it interesting, 4 minus x squared when x is less than or equal to 1, and sure, 2x plus 1 when x is greater than 1. And the question I want to ask is this function continuous at x equal to 1? Meaning, can I draw the graph without looking at penalty paper? So I know from the left side, right, I've got 4 minus x squared, which is this kind of deal, and stopping somewhere like there. And then from the right side, I've got 2x plus 1, which, I don't know, might be something like this. So the question is, do I have a jump here or not? And the way we kind of figure it out is we look at the limit from either side. So to tell if the function is continuous, we actually check 3 things usually, which he wrote as one thing, which it is one thing, but we have to check. Does the limit as x approaches 1 of f of x equal the function value, f of 1? And the way we usually kind of think about checking this is by checking 3 things. We first ask ourselves, does f of 1 exist? Well, yes, I can plug in 1. If I plug in 1, I'm going to plug into the top part. That's where x is equal to 1. F of 1 is 4 minus 1 squared, which is 3. Okay, the second part is, does the limit exist? And that's where we look at the limit from either side. The limit as x approaches 1 from the left, we're going to use the top piece because that's where x is less than 1. We We still just get to use the direct substitution method and plug in 1. We get 4 minus 1 squared, which is 3. And then we look at the limit as x approaches 1 from the right of f of x. That's the limit as x approaches 1 from the right of, we're going to use this p cut for x is bigger than 1. And then we can just plug in 1 and we get 2 times 1, which is 3. So does the limit exist? Yes, because the left-hand limit and the right-hand limit. So we can say, oh yeah, the limit as x approaches 3 of f of x, sorry, as x approaches 1, apologies, is equal to 3. And then the final question, which we already can see the answer to, is, are they the same? Does this happen? Does the limit as x approaches 1 of f of x equal f of 1? And the answer is yes, right? F of 1 was 3 and 1 was 3. So actually, my function looks like this. So it is continuous. Right? There are no breaks when you draw the graph. This and then that. But this is the usual kind of methodology for trying to show a function is continuous somewhere. Is you ask yourself, does the function exist? If the answer is no, then it's not continuous. If the answer is yes, you move on to, does the limit exist? If the answer is no, then it's not continuous. If the answer is yes, you move on to, are they the same? If the answer is yes, then it's continuous. All right, so that's all I've got for today. I imagine on Wednesday we'll talk more about continuity, and we'll probably start talking about the definition of the derivative. There's the attendance form one more time. Please make sure you fill it out. All right, see you guys Wednesday. Take care. And you're all very welcome. Oh, there's a quiz. Do the quiz.